Hi friends, I am Rajesh. Welcome to my channel, Rajesh's Max Class. Today, I am going to take the topic nested intervals. Clear? Nested intervals. Nested intervals is the collection of intervals that is set upon In such that n belongs to n. Collection of intervals having the property I1 superset, I1 superset, I2 superset, I3 superset, etc. superset, In superset, In plus 1, superset, etc. Clear? I1 superset, I2 superset, I3 superset, etc. Clear? So nested intervals is the collection of intervals having the property I1 superset, I2 superset, etc. Clear? That means I1 contains I2, I2 contains I3, I3 contains I4, etc. Clear? That means here if we move from left to right, the size of each interval is decreasing. Clear? Generally, we can write In superset In plus 1, In superset In plus 1 for all n belongs to capital N. For all n belongs to capital N. Clear? If we put n equals 1, then this becomes I1 superset I2. Put n equals 2, this becomes I2 superset I3. Put n equals 3, this becomes I3 superset I4. So generally we can write In superset In plus 1 for all n belongs to capital. Clear? For example, In equals closed interval minus 1 by n, comma 1 by n. Here n belongs to capital N. Capital N means the set of natural numbers. Clear? We can draw the real line minus infinity to plus infinity, center 0. Okay. First we put n equals 1, then this interval becomes I1 equals minus 1 comma 1. I1 equals minus 1 comma 1. So this is I1. Minus 1 to plus 1. Closed interval minus 1 to plus 1. So this is I1. I1. Clear? Next put n equals 2. Then I2 equals closed interval minus 1 by 2 comma 1 by 2. I2 equals closed interval minus 1 by 2 comma 1 by 2. So this is I2 minus 1 by 2, 1 by 2. This is I2. Here I1 contains I2. Next put n equals 3. Then this becomes I3 equals closed interval minus 1 by 3 comma plus 1 by 3. So this is I3 closed interval minus 1 by 3 comma 1 by 3. This is I3. So here I2 contains I3. Put n equals 4. We will get I4, etc. Clear? That means I1 contains I2, I2 contains I3, I3 contains I4, etc. Clear? That means I1 superset, I2 superset, I3 superset, etc. Clear? So this is the example for nested intervals. Clear? We can take another example. In equals open interval 0 comma 1. Open interval 0 comma 1 by n. Open interval 0 comma 1 by n. Here n belongs to capital N. Clear? Okay. Once again, we can draw the real line minus infinity to infinity and center 0. So first we put n equals 1. N equals 1. Then this becomes I1 equals open interval 0 comma 1. So this is I1. Open interval 0 comma 1. This is I1. Clear? Next put n equals 2. Then this becomes I2 equals open interval 0 comma 1 by 2. 1 by 2. Open interval, this is 1 by 2. So open interval 0 comma 1 by 2. So this is I2. I2. So here I1 contains I2. Clear? Next put n equals 3. Then we will get I3. I3 equals 0 comma 1 by 3. So this is I3. 0 comma 1 by 3. I3. Clear? Etc. Etc. So I1 contains I2, I2 contains I3, etc. Clear? This is also another example for nested intervals. Clear? Okay. Next we will discuss about a property. Nested intervals property. Nested intervals property. Nested intervals property. Clear? Nested intervals property. Clear? The statement is, if In equals closed interval a n comma b n n belongs to capital N is a nested sequence of closed bounded intervals. Closed bounded intervals. Then there exists a number psi belongs to R. Then there exists a number psi belongs to R such that psi belongs to IN for all n belongs to capital N. Psi belongs to IN for all n belongs to capital N. Clear? This is the nested intervals property. The statement is, if IN equals closed interval AN comma BN, here n belongs to capital N, is a nested sequence of closed bounded intervals, then there exists a number psi belongs to R such that psi belongs to IN for all n belongs to capital N. Clear? Okay. Already we have seen set for IN such that n belongs to capital N. Here IN equals, if we take IN equals closed interval minus 1 by n comma 1 by n, closed interval minus 1 by n comma 1 by n, then this collection is a nested intervals. Clear? This collection is a nested intervals. In this case, we have, this is I1 minus 1 2 plus 1, and this is I2, this is 0, etc. Clear? I1, this is I2, etc. Clear? Here we can say that 0 belongs to IN for all n belongs to capital N. For all n belongs to capital N. Clear? In this example, we can see 0 belongs to IN for all n belongs to capital N. That means 0 belongs to I1, 0 belongs to I2, 0 belongs to I3, etc. That means 0 is a common point in all intervals. 0 is a common point in all these intervals. Clear? That means 0 belongs to I1, 0 belongs to I2, 0 belongs to I3, etc. That means we can write 0 belongs to IN for all n belongs to capital N. So here we can type psi equals 0. Psi equals 0. Clear? Clear? Okay, psi equals 0. That means we can say that we find a real number 0 or real number psi such that psi belongs to IN for all n belongs to capital N. Clear? But if we take IN equals open interval 0, 1, open interval 0, 1, open interval 0, 1 by n, open interval 0, 1 by n. This collection is also nested intervals. If we take IN equals open interval 0, 1 by n, then this collection becomes nested intervals. In this case, we have, this is 0, so this is I1, and this is I2, open interval 0, 1 by 2, I2, I3, this is I3, clear? Okay, 1 by 3, clear? In this example, we can say that there does not exist psi, there does not exist a real number psi, there does not exist a real number psi such that psi belongs to IN for all n belongs to capital N. Clear? In this case, we can say that there does not exist a real number psi such that psi belongs to IN for all n belongs to capital N. Clear? That means we cannot find a real number psi such that psi belongs to all, psi is a common element in all these intervals. That means psi belongs to In for all n belongs to capital N. Clear? So what is the reason? In this case, we have each interval is open bounded. Each interval is open bounded. But in the previous example, that is In equals closed interval minus 1 by n comma 1 by n. Here, each interval is closed bounded interval. Closed bounded interval. So, this condition is necessary. This condition is necessary. Closed bounded intervals. Clear? Okay. That means this is the important part in this theorem, this statement, closed bounded intervals. Proof. Clear? Here, given In equals closed interval an comma bn is a nested sequence of closed bounded intervals. So we can write I1 superset I2 superset I3 superset etc. What is I1? I1 is closed interval a1 comma b1 superset I2 closed interval a2 comma b2 superset etc. Suppose if we draw a real line, then we have this is I1, that means closed interval a1 comma b1 a1 comma b1, and this is a2 comma b2 a3 closed interval a3 comma b3. Clear? Etc. Clear? Okay. In this case, we can say that a1 is less than or is equal to b1, a2 is less than or is equal to b1, a3 is less than or is equal to b1. Clear? That means each an is less than or is equal to b1. Clear? Each an is less than or is equal to b1. We can write an is less than or is equal to b1 for all n belongs to capital N. For all n belongs to capital N. a1 is less than or is equal to b1. Put n equals to, then a2 is less than or is equal to b1. That means each an is less than or is equal to b1. Clear? If we take the set of all an, such that n belongs to n, then we can say that b1 is an upper bound of this collection. b1 is an upper bound of this collection because every element in this collection is less than or is equal to b1. Clear? So b1 is an upper bound of this collection. Clear? Okay. So here we can write b1 is an upper bound. b1 is an upper bound of set of all an such that n belongs to capital N. Set of all an such that n belongs to capital N. Clear? Next, here we will apply the supremum property of R. Supremum property of R. What is the supremum property of R? Supremum property of R. Supremum property of R. The statement is every non-empty set of real numbers, every non-empty set of real numbers that has an upper bound has a supremum in R. Clear? This is the supremum property of R. Supremum property of R. Every non-empty set of real numbers that has an upper bound has a supremum in R. Clear? Here, set of all an such that n belongs to n is a non-empty subset of R, and it has an upper bound. That means this collection is bounded above. Here, b1 is an upper bound of this collection. So, by the supremum property of R, we can say that this collection has a supremum in R. We denote it by psi. That means supremum set of all an such that n belongs to capital N equals psi. Psi is a real number. Psi belongs to R. Clear? So we can write supremum self-found AN such that n belongs to capital N equals psi, where psi is a real number. Psi belongs to R. Clear? So we get supremum self-found AN such that n belongs to capital N equals psi. Clear? That means supremum means least upper bound. Psi is the supremum of the set-found AN such that n belongs to capital N means psi is a least upper bound. Psi is a least upper bound of set-found AN such that n belongs to capital. Clear? Psi is the least upper bound of set-found AN such that n belongs to N. That implies psi is an upper bound. Psi is an upper bound. Psi is an upper bound of set-found AN such that n belongs to capital. Clear? Set-found AN such that n belongs to capital. Psi is an upper bound. Psi is an upper bound of set-found AN such that n belongs to capital. Clear? By the definition of an upper bound, we can write AN is less than or is equal to psi. AN is less than or is equal to psi for all n belongs to capital. Clear? Because psi is an upper bound of set-found AN such that n belongs to N. Then by the definition of upper bound, every element in this collection is less than or is equal to psi. That means we can write AN is less than or is equal to psi for all n belongs to capital. Clear? So here we can write AN is less than or is equal to psi. AN is less than or is equal to psi. Clear? For all n belongs to capital. Clear? AN is less than or is equal to psi for all n belongs to capital. Clear? Okay. Once again, we use IN is a nested sequence of closed bounded intervals. So we can write I1 superset, I2 superset, I3 superset, etc. Clear? Okay. So this is our real line. Here this is I1, that means closed interval A1 B1, and closed interval A2 B2, this is I2, A3 B3, closed interval A3 B3, this is I3. Clear? Okay. Next, we take any particular Bn, here n belongs to capital, any particular Bn. Okay. Next, we will prove Bn is an upper bound of the collection set-found AK such that K belongs to N. Set-found AK such that K belongs to N. Clear? Next, we will prove Bn. Next, we will prove Bn is an upper bound. Bn is an upper bound of set-found AK such that K belongs to capital. Set-found AK such that K belongs to capital. Clear? Okay. Here there are two cases. The first case, small n is less than or is equal to K, n is less than or is equal to K, and the second case, n is greater than K. Clear? There are two cases. The first case, n is less than or is equal to K, and the second case, n is greater than K. Clear? So the first case, so n is less than or is equal to K. In this case, we can write IN superset IK. Here n is less than or is equal to K. Clear? By the definition of nested intervals, we can write In superset Ik. Clear? In superset Ik. That means In contains Ik. Here n is less than or is equal to k. Then by the definition of nested intervals, we have In contains Ik. Clear? So we can draw these intervals. So this is In, that means closed interval An, comma Bn, and In contains Ik. So this is closed interval AK, comma BK. Clear? In this case, we have AK is less than or is equal to BK, and BK is less than or is equal to Bn. Clear? We can write AK is less than or is equal to BK, which is less than or is equal to Bn. Clear? In this case, we have AK is less than or is equal to BK, and BK is less than or is equal to Bn. Clear? Okay. That means we can write AK is less than or is equal to Bn. Clear? AK is less than or is equal to Bn. Clear? AK is less than or is equal to Bn. Clear? So here we get, if n is less than or is equal to k, then AK is less than or is equal to Bn. Clear? If n is less than or is equal to k, then AK is less than or is equal to Bn. So we can write AK is less than or is equal to Bn if n is less than or is equal to k. N is less than or is equal to k. Clear? AK is less than or is equal to Bn if n is less than or is equal to k. So next case, n is greater than k. 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 In this case, we have Ik superset In. Ik superset In. Here n is greater than k. N is greater than k. Then by the definition of nested intervals, we have Ik contains In. Ik contains In. Clear? Here n is greater than k. Then by the definition of nested intervals, Ik contains In. Clear? Okay. So we draw the real line. So this is AK comma BK, closed interval AK comma BK. That is Ik. Here we have Ik contains In. So this is An, closed interval An comma Bn. That means In. Clear? In. Closed interval An comma Bn. Okay. In this case, we have AK less than or is equal to An. AK less than AK. In this case, AK is less than or is equal to An, and An is less than or is equal to Bn, and An is less than or is equal to Bn. Clear? Here AK is less than or is equal to An, and An is less than or is equal to Bn. Okay. So we get AK is less than or is equal to An, which is less than or is equal to Bn. So we can write AK is less than or is equal to Bn. AK is less than or is equal to Bn. Clear? That means in this case, we get AK is less than or is equal to Bn. That means if n is greater than k, then we get AK is less than or is equal to Bn. So we can write AK is less than or is equal to Bn if n is greater than k. Clear? Okay. So in each case, we get AK is less than or is equal to Bn. First we get AK is less than or is equal to Bn if n is less than or is equal to k. Next, we get AK is less than or is equal to Bn if n is greater than k. Clear? In either case, we have AK is less than or is equal to Bn. Clear? AK is less than or is equal to Bn. So we can write AK is less than or is equal to Bn for all k. For all k belongs to capital. For all k belongs to capital. Clear? Okay. In either case, we have AK is less than or is equal to Bn. So we can write AK is less than or is equal to Bn for all k belongs to capital. Okay. AK is less than or is equal to Bn. Clear? Okay. In this case, we can say that Bn is an upper bound of this collection. Bn is an upper bound of this collection because every element in this collection is less than or is equal to Bn. Clear? Every element in this set is less than or is equal to Bn. So we have Bn is an upper bound of the set of all AK such that K belongs to N. Clear? Once again, here AK is less than or is equal to Bn for all K belongs to capital N. That means every element in this collection is less than or is equal to Bn for all K belongs to capital N. By the definition of an upper bound, we can say that Bn is an upper bound of the set of all AK such that K belongs to capital N. Clear? Okay. So we have Bn is an upper bound of set of all AK such that K belongs to N. Also we have psi is a least upper bound. Psi is a least upper bound. Psi is a least upper bound of set of all An such that N belongs to capital N. Psi is a least upper bound of set of all An such that N belongs to capital N. Here we know these two sets are equal, same. These two sets are same. So we have Bn is an upper bound of this collection and Xi is the least upper bound of this collection. Clear? So what is the relation between Xi and Bn? Here Xi is the least upper bound of this collection. Xi is the least upper bound of this collection. Bn is an upper bound of this collection. These two sets are equal. Then we can say that Xi is less than or is equal to Bn. Once again, Xi is the least upper bound of this collection. Bn is an upper bound of this collection. So Xi is less than or is equal to Bn for every n belongs to. We can write for every n belongs to. For all n belongs to capital. Because here Bn is an arbitrary element. So we can write Xi is less than or is equal to Bn for all n belongs to capital. Clear? Okay. Next, combining these two inequalities. Already we have An is less than or is equal to Xi for all n belongs to capital N. Clear? Here we get Xi is less than or is equal to Bn for all n belongs to capital N. Clear? Combining these two inequalities, then we can write An is less than or is equal to Xi and Xi is less than or is equal to Bn for all n belongs to capital N. For all n belongs to capital N. Clear? For all n belongs to capital N. An is less than or is equal to Xi, which is less than or is equal to Bn for all n belongs to capital N. That means we can write Xi belongs to closed interval An comma Bn, closed interval An comma Bn for all n belongs to capital N. That means Xi belongs to, what is it? Closed interval An comma Bn, In. So Xi belongs to In for all n belongs to capital N. For all n belongs to capital N. Clear? Xi belongs to In for all n belongs to capital N. This is the nested intervals property. If In equals closed interval An comma Bn, where n belongs to capital N, is a nested sequence of closed bounded intervals, then the X is a number Xi belongs to R such that Xi belongs to In for all n belongs to capital N. Clear? Okay. So I hope you have enjoyed my class. Thank you.